Good afternoon, ladies and gentlemen. Welcome to the Hong Kong University of Science and Technology. We are honored to have Professor Reinhard Genzel, the laureate of the 2008 Shaw Prize in Astronomy, to deliver the prize lecture here. The Shaw Prize is an international award established under the auspices of Sir Run Shaw to honor individuals who are currently active in their respective fields and have made distinguished impacts. The fields are astronomy, life science and medicine, and mathematical sciences. The award is dedicated to the furthering of society good, enhancement of quality of life, and the enrichment of human spirit. Now, may I invite Professor Paul Chu, the president of our university, to introduce our speaker.
Good afternoon. I welcome all of you to come to the Shaw lecture this afternoon. Especially, it's a great honor to have our Shaw laureate this year, Professor Reinhard Genzel, to give the lecture here. I personally would like to extend, because Professor Genzel received his undergraduate study, a PhD from University of Bonn, and then later on went to University of California at Berkeley as the Miller Professor. And he stayed there for a little while, and then later on went back to Germany as the director of Max Planck Institute over there. And so personally, I would like to extend my warmest welcome to all of you again at today's Shaw lecture to be given by Professor Reinhard Genzel, director of the Max Planck Institute for Extraterrestrial Physics and professor of physics of the University of California at Berkeley. Professor Genzel will be speaking on the most exciting and intriguing subject, the discovery of a supermassive black hole at the center of our galaxy, Milky Way, for which Professor Genzel was awarded the 2008 Shaw Prize in Astronomy. It has been speculated for almost 40 years that the Milky Way must contain a supermassive black hole at its center. But evidence was hard to come by. To prove this conjecture, Professor Genzel developed state-of-the-art astronomical instrument and carried out a persistent program of observing our galactic center for many years, which ultimately led to the discovery of a black hole a few million times the mass of our sun in the center of our galaxy. Supermassive black holes are now recognized to account for the luminous sources seen at the nuclei of galaxies and to play a fundamental role in the formation of galaxies. And Professor Genzel's lecture today will reveal to us this secret of the universe. A few days ago, the university unveiled on our campus a replica of armillary sphere, an ancient Chinese instrument used to observe the universe. Professor Genzel's instruments are certainly much more sophisticated than that. However, both reflect genuine minds and spirit of curiosity, aspiration, and steadfastness in scientific discovery. Today, I'm really delighted to see many young and curious faces among our audience. I'm sure that all of you will learn from Professor Genzel and come away filled with inspirations, especially me. Ladies and gentlemen, it's my great honor to present to you one of the greatest astrophysicists of our time, Professor Reinhard Genzel.
Thank you, Professor Chu. Before the lecture, we would like to present a souvenir to Professor Genzel as a small token of our appreciation. The souvenir is a miniature replica of the mural carved on the side of our sundial podium, this big red bird right outside. The mural depicts 39 ancient Chinese science and technology achievements. Among them is the armillary sphere that Professor Chu just mentioned. This was the principal astronomical instrument before the invention of telescope. The earliest of such instrument was made by the Chinese in the 4th century BC. Thank you, professors.
Let me say something about it.
Okay, now may I invite Professor Genzel to start the lecture.
Thank you very much. Dear Professor Chu and colleagues, and all the many people who have come here. I've seen this mural earlier today, and I was very much impressed by it. I'm a very great admirer of the Chinese culture. China has done so much to bring humankind forward in long times past, and the more it's, I'm sure, exciting for the world to see you come back into your own and really become world leaders. And we in Europe see this with great admiration. The Olympic Games were just a case show for your country, and I think you have many things to be proud of. Just go on this path. So my talk is about black holes. Now, many of you, of course, are perfect experts in black holes, I'm sure, because you've seen many science fiction movies. But I promise you, what we've been doing actually goes a little beyond what you can see in the science fiction movie. It's real science. It's hardcore experimental work now to really look at objects which we suspect might contain these enormous concentrations of mass. And I'll show you the story which has evolved over the last years, having to do with the work my group and I have been doing, as well as colleagues, but also the ramifications to bigger things, namely, how, for instance, galaxies formed and evolved. Now, let me start by saying that the work which my group has done, in particular on the galactic center, is on an object which, on astronomical scales, is fairly close by, 26,000 light years away. It's fairly nearby on the cosmic scales. But unfortunately, actually, the center of our Milky Way is very hard to spot, even from Hong Kong. Not because of the light pollution, but because we, in the Milky Way galaxy, sit in the plane. Our sun, the Earth, sits in the plane of that galaxy. And as we look at the galactic center, and there's a picture, in fact, of the galactic center seen in the southern skies. This is in Chile. Perhaps we could have the lights down a little bit, see it a little better. You see the plane of the Milky Way, which many of you, I'm sure, have spotted. And you see a concentration here of a lot of light here in the very center. That's the so-called bulge of the Milky Way. That's where a large concentration of stars is. But the galactic center itself you cannot spot. So that's why we built an instrument at the VLT, which I'll show you later, to show you what the galactic center is. And this is a big laser, and we use that here as a laser pointer. We have other purposes for it too, but this shows you where the galactic center is, behind that dust, which in fact is between us and the Milky Way. So why are we interested in this question? And let me start and take you on a little journey. And may I have the light off really completely? Please. Okay, wonderful. So this is a wonderful movie to have a little journey from our neighborhood. You see here dust and gas clouds of young stars forming in the neighborhood of the Milky Way. And we are flying out. You see all these many stars in the vicinity. By the way, the speed at which we're going, we cannot reach in reality. This is 10 to the 12 times the speed of light. The galaxy is big, but computers can do everything. So we can actually fly through the Milky Way and above it. So we are rising now above the plane of the Milky Way. There's the center. That's that bulge. That's where the black hole story will evolve. And we're flying away from the Milky Way and seeing other nearby Milky Way centers. Most of the stars, almost all of the stars in the universe, are in these island universes, in these Milky Ways. Typically 100 billion stars in each one of these Milky Ways. And the galaxies are grouped together in large clusters. Here you see in the background here a very big cluster as we fly by some of our nearby galaxies. The distances between galaxies is very large, typically 1 million light years. So this is long distances. Now what astronomers have learned over the last 20 years is in addition to all these stars in these galaxies, there appear to be in the centers concentration of material, which, as you will see from this talk, are probably black holes. And so the question we have is, how did this all form? How did this all come together? How did these black holes come about? When were they formed? And why, perhaps? And what does it have to do with the evolution of the galaxies? Now, before I go on and tell you this story, let me first, however, tell you a little bit more about black holes, because you might wonder exactly what is it about black holes. Now, black holes are very simple things as far as I'm concerned. They are objects which have an enormous concentration of mass. And in fact, already in the 18th century, Reverend John Mitchell at Cambridge, England, considered the idea, well, suppose you have an object which has the mass of the sun, but is very much smaller. Now, he knew Newtonian physics and could calculate the escape speed a rocket might have to achieve in order to get off that star to infinity. You can do this yourself if you have some, basic college physics. To get away from the Earth, you need about 30,000 kilometers an hour. But if you make the sun as small as 3 kilometers, well, that speed, you can easily calculate, becomes the speed of light. So Mitchell, already in 1783, calculated that such a star, if it were to exist, would not be visible because not even light would be able to escape from its surface. So there it is. That's a black hole. Now, that is, however, the wrong physics, it turns out, although it gives roughly the right answer. It took much longer, and in fact, Mitchell's speculations were forgotten for a long time. It took until Albert Einstein invented in 1915 and 16 the general relativity theory of gravity, which describes the action of masses on the the geometric structure of space-time. And with this theory in hand, in fact, Karl Schwarzschild, who died actually, unfortunately, just a year later in the war, found the first solution for a spherically symmetric mass distribution in the Einstein metric. That's the Schwarzschild metric. And that solution of Einstein's equations says the same thing which I just told you, but in more complicated terms, and says in addition that any object could be a black hole, any mass can be a black hole, as long as its concentration initially is greater than a certain amount, its size is smaller than a certain amount. And that size, that event horizon, for the sun indeed is 3 kilometers. For the Earth, by the way, it's 1 centimeter. So if you would compress the Earth to 1 centimeter, it would be a black hole. Now, this is the mass of a black hole. There's a second property a black hole can have, and that's spin, rotation. And so it took, in fact, believe it or not, another almost 50 years or 45 years until the full solution, including the spin, was found by Roy Kerr. Now, these are classical solutions of general relativity. Beyond that, of course, we suspect, and we are fairly sure, many physicists are sure, that in the centers of black holes, which we cannot communicate with, there must be very fascinating things going on, because there you have, according to general relativity, a singularity of mass. which most people suspect cannot be true. Also, and that is Steve Hawking's work, black holes may not be as black as they think, as you might think, at least in the quantum world, because Heisenberg's uncertainty tells you that, for small enough periods of time, some energy can sort of jump out of black holes. So Hawking radiation can play a role, but mostly for small black holes. For the ones which we are studying, that does not play a role. So this is all a body of tremendous theory which was built up over the last century, but evidence for black holes remained very uncertain until about 1960s. Then in the 1960s, a number of things happened. First, quasars were discovered. And I'll tell you that story just in a few minutes. Next, the X-ray astronomers found with their first rockets and satellites strange objects which turned out to be binary objects. One of the binaries then was speculated to be a stellar black hole. So black holes became an interesting kind of a thing, and also paradoxically the brightest objects. And you might be very surprised to hear that while black holes are black in the sense that nothing can come out of them, when you fall into a black hole, on your way before you're out inside of the no return land, radiation can be produced at the highest efficiency we can think of. In fact, about 40% maximum of mc squared can be radiated. And that, in fact, that high efficiency of energy creation was the reason why black holes came about as a matter of speculations in the case of the quasars. Let me describe the quasars. It was about 1960 when the radio astronomers, particularly in Cambridge, England, were discovering their first objects, their first radio stars. And the radio astronomers began wondering, what are these objects? And so on pictures, optical pictures, some of these objects looked like stars, very compact, stellar-like objects. But then Martin Schmidt discovered in one of these radio stars that the spectral lines, which were clearly visible there, were shifted in a strange way. And he deciphered that shift just to do a redshift of the spectrum of hydrogen and helium and a few other elements. And then they looked at other quasars, and again, they found the same thing. Now, redshift means, in the sense of motion, that there's a Doppler shift, that something is moving. And already then, of course, it was known that galaxies move apart due to the cosmic expansion. So the application of the cosmic expansion to these objects means that they're very far away, such that this little speck here, which is hard to detect at the time anyhow, actually is about 1,000 times brighter than an entire Milky Way. So these are extremely luminous objects. The quasars, most luminous quasars, the brightest objects in the universe. So how can that be? Now, there are pictures nowadays which are much better than what was possible at the time from Hubble Space Telescope of some of the nearby quasars. Here's one of them. You see a very bright, overexposed spot. That's actually the quasar. But that's not the reason I'm showing you the picture. I'm showing you the picture because you might see around this quasar what looks like sort of an ordinary galaxy. And indeed, we now know that in all cases where this has been possible, quasars are the nuclei of galaxies, big galaxies. They are very compact, in most cases unresolved spots of enormous density of light in the centers of Milky Way systems. And so how do you create this much light? 1,000 times, 10,000 times more light than an entire Milky Way. Maybe, that was the speculation initially, you could have a concentration of stars. You can calculate, given that fusion from hydrogen to helium produces about 0.5% of mc squared, how much energy you can release if you pack a certain number of stars into a central region of a galaxy. And what you find is it's not possible, under any means, to power one of these quasars for any length of time. So the theorists were puzzled. It was then Donald Lindenbell, Martin Rees, Ed Salpeter, who then hit on the idea, well, wait a second. We know that when you let material fall into a black hole, on its way in, you can release all of that gravitational energy, or at least 40%, 10% of mc squared, up to 40% mc squared. So that's a factor of 100 more than in fusion. So obviously, you can use these black holes as energy creation machines. And so that's how the standard models of accreting black holes explaining quasars was born. But that's a speculation, if you like, a plausible one at that. And there was other evidence in favor of it. Very hard radiation was discovered. Radio astronomers discovered radio jets. These are streams of relativistically moving plasma away from nuclei of such quasars. So as far as the astronomers were concerned, by the 1980s, it was pretty clear that the accreting black hole models for these quasars was very, very plausible. But the proof really of this is you have to show that at the center of these quasars is a mass whose concentration is large enough that it has an Einstein property of an event horizon. It's a black hole. Now that experimental proof, that observational proof, cannot be done in quasars. They're so far away. But they can be done, perhaps, in a much closer system. And that's where the center of our Milky Way comes in, although it is by no means a quasar. So how do you make something seen which you cannot see? Okay, well, it's very simple. Think of Kepler. Kepler analyzed the data of Tycho Brahe in the 17th century and found Kepler's laws, which basically state that when you look at the motions of the planets, that the further away a planet is from the sun here in the center, the slower it moves. That's Kepler's laws. The velocity goes like 1 over the square root of the distance. Now, this law holds whether or not the sun shines. So suppose for a moment that, Tycho Brahe had given Kepler the data, but the sun would not be shining. Kepler would have had to come to the same conclusion as he did, namely that there is a mass in the center of the solar system of 1 solar mass. Now, he wouldn't have known at the time that it could be or could not have been a black hole. In fact, the sun is not a black hole, because in order to prove that it's a black hole, there would have to be planets which are yet further in, such that you can be sure that the concentration of that object is really so large that it cannot be anything but a black hole. But that's the principle, how we sense, how we test the gravitational field of any object if you have these test particles. And what we do in the galactic center is we use not planets, but stars or gas. And we measure their motion of these stars as far into where we suspect there might be a central black hole as possible. And if you're lucky and nature is good to us, maybe it gives us trace particles which are so close that we can exclude anything but a black hole. That's the story I will tell you. So the galactic center, as I said already, is reasonably far away from us. The sun is out in a spiral galaxy here in the center of 26,000 light years away from. That's where we're looking. Now, the first evidence that there might be indeed something in the galactic center akin to a mass concentration came from work in Berkeley, in fact, in the 1970s by Charles Townes, who has already been mentioned today. At the time, radio astronomers already had been able to discover the first pictures of the radio emission. This is a radiograph, a radio image, which nowadays can be done very, very well with so-called radio interferometers. This is a radiograph of centimeter emission from hot electrons and protons in the galactic center. This is hot gas. In the center of this hot gas, you see there's a spot, a very bright spot. In fact, this spot is tremendously overexposed on this picture. And the radio astronomers discovered that this spot here is extremely small. It has a size in the radio region of only about the Earth diameter, the distance between the sun and the Earth, so 1 astronomical unit. That's extremely compact. It's almost stellar and very, very bright in radio waves. So most people started speculating, well, maybe there's a black hole there. Quasars had been discovered at that time, so people said, well, if there are massive black holes in quasars, maybe there should be a black hole in every galaxy also here. So the galactic center, and its role now, is sort of a laboratory to test ideas, concepts, which we might then apply to other objects, which are much further away. The next quasar, by the way, is about 10,000 to 50,000 times further away than the galactic center. So measurements which we can make here with the best instruments we now have are not possible in the distant quasars. And here are our test particles, okay? So this region here in the radio is intensely populated by stars, and we are using these stars to measure the potential of the black hole. So the evidence at the time, which Professor Towns had, did not come from stars, but from gas. And he used spectroscopy of infrared lines to measure the shapes and positions of lines. This is a line of ionized neon in the 10 micron region. And if you look at the shapes of these lines, what you discover is you move from one spot to another around this radio source. The lines move around. And they move around by an amount which, if you interpret it as a Doppler effect, corresponds to several hundred kilometers per second. The Earth moves around the Sun with 30 kilometers per second. So this is at least 10 times faster. So that tells you if there's something mass which causes that motion, well then this mass has to be great. In fact, the calculation which came out here was about 3 million solar masses is required. That was in 1977. Now, this is 30 years later. What I report to you today is a measurement of a mass of this object, which turns out to be 4 million solar masses. So Towns knew it already 30 years ago, and the rest was details. So what we did, and this is a bit of our team, which played a very important role here. Some of the individuals, in fact, are in the room here. Is we build instruments, ever better instruments, and put them on bigger and bigger telescopes in order to get very sharp images of the galactic center, also measure the spectra of objects in the galactic center, and over time, with ever greater precision, by a factor of 1,000 in this period of 20 years where we did this experiment, assembled a case that indeed Sagittarius star, that radio source, is a massive black hole. And one of the key things here, oh, that's very good. That's superb. That always happens to unlucky presenters, where then they have to tell jokes in between. Do I know of any jokes? No. Let's see how fast we can recover here. Okay, not bad. So this is an image, in fact, in the infrared of the central light year. You see this bar is 1 light year in the center of our Milky Way. Now in the infrared, I should say, initially, when we started all of this, one had not good cameras, not good CCD cameras like you're used to in the optical. But that has changed. Nowadays, we can take pictures in the infrared just as much as you can take pictures in the optical. So what you see in front of you is a picture at several infrared wavelengths, so that's a color image, at wavelengths which are about 4, 5, 6 times longer than the light you see with your eyes. The arrows here denote where Sagittarius radio source. That's our culprit. So from now on, watch for those arrows. That's where, here X spots, marks the spot, and so that's where we want to look. So our goal, remember, is that we would like to use these stars as trace particles and measure their motion on the sky as well as through Doppler velocity and see whether there's a Kepler law here, which would tell us that there's a mass. Now there's a problem. The problem is this is all pretty blurred. Now this picture is taken with an 8-meter telescope. Should be much sharper. What's the problem? The problem is that we are sitting on Earth. And as we look up in the sky, we're looking through the Earth atmosphere, which is turbulent. And, when you look along a hot road in Hong Kong summer, it's, blurs the pictures of distant cars, etc. Same thing is happening in the atmosphere. So we don't get the full sharpness of a big telescope. what do? Well, we put it up in space. That's one solution. Very costly, and you get only a 2-meter class telescope. That's the Hubble. No, but what about a big telescope? Well, we pull ourselves out of the swamp, and that is called adaptive optics. When you take pictures in very rapid succession, and maybe you can see this here, of this field, you can see that actually on any one of the short exposure images, there is still structure here of these individual stars. The reason why these star images are so smeared out is that over time, the Earth atmosphere destroys all the sharp information. But if you take sharp enough, fast enough images, or control the wavefront, then you can overcome the blurring of the Earth atmosphere. And that is called adaptive optics. And so when we look at a modern adaptive optics system where you do this control of the Earth atmosphere online, you can actually take the smeared out image and pull it together to a spot which in fact then corresponds to the full sharpness of the large telescope. So this is a wonderful technique, requires very fast electronics and optomechanics to really work, but it does work. And so then you start with an image like this, you switch on the AO, and things become much clearer, by about a factor of 30, okay? So it becomes much, much sharper, and also at the same time much deeper. So you not only you get sharper images of the stars, but you also can see fainter images of the star. So that technique really has been a key element of our work. And now with images like this, we can begin to work and look for the black hole. We can take pictures like this every week or every year initially, and then follow over time and look for changes in the positions of stars. We can take spectra of individual stars and look for the Doppler motions of the gases in them. And now I'll show you what we found. So here, this is the sort of very central region with one of these very high resolution AO adaptive optics images. That cross here denotes Sag star again. You see there are a bunch of fainter stars in the vicinity. Now we are down to a light month, by the way. We used to be at a light year. Now we're down to a light month. And as you will see, we can go closer and closer as we get better and better measurements. A light month. So what I do now is show you images from 3 years in 3 different colors. So red is 2003, green is 2004, and blue is 2005. And you would immediately see and agree with me that this star, for instance, moved, right? Because the different colors don't show the same position. If you look out here, there's a star where looks pretty white. That means it hasn't moved. Now look at the different stars. There is Sag star. Wouldn't you agree with me that as you go from inside out, these prism effects, these spectra, decrease in quality? Get less and less. As you go further in, you see more of these, these prisms. What does that mean? That means that the stars inside move faster than outside. In fact, statistically, it's exactly a Kepler law, 1/√r, down to a scale which now is a fraction of a light month. That was where we were about 10 years ago. 10 years ago, we found that, and when we said, well, if you look at these motions again, by the way, you measure the mass immediately and you find about 3 million solar masses, the same number which I've said already, but now on a scale of 10 light days or so. And that immediately said that mass must be really very concentrated. Was it really a black hole? Well, there were some alternatives still left. So how could we improve on that? To be really sure, well, we have to go further in. Now, how can you go further in? You have to have yet higher resolution and or better data. What could we do to improve on these motions? Well, if we had orbits, if you could actually measure the precise information on orbits of each star, and if some stars would make it very close to the center, well, then we could make progress. And we were dreaming. In fact, in '96, when we had the first Nature paper out, we in fact did create some movies. And those movies had time scales of about 100 years on them, time scales of generations of astronomers. But sometimes nature is good to us. And in fact, we kept on observing, and within just a few years, we found for one of the stars and then for ever more of these stars, actual orbits. That's remarkable. Let me show you one of the best case we now have. That's this star here. So Sagittarius star is this group of green points, which I won't describe in more detail. So here, that's when we started our experiment in '92. And then we kept on measuring. And initially, everything was reasonably boring. The star moved at 400 kilometers per second or so, which is fast, but not that fast. And then, in fact, when we started with the VLT measurements, all of a sudden the star was on the other side of Sagittarius star. You see, he always was on that side, and bang, and here it was on the other. I tell you, that was one of these moments, these rare moments a scientist has, and you cannot expect it to have, where you have, wow. Because, you just go, plot this, you take your ruler, you take Kepler's laws, and you know everything. You don't need a big computer. Now, of course, we were using a big computer afterwards, but the point is, this is a fairly direct result, which shows us that this star is on an elliptical orbit, which at the closest distance here was only about 15 light hours away from Sagittarius star. 15 light hours is the distance of 3 times the orbit of Neptune. So that's solar system scales. But it was moving then at about 8,000 kilometers per second. So about several hundred times the speed of the Earth around the Sun. So that was a very fast speed. Since that time, in 2002, the thing has been moving out and getting slower. It now has made it once around. So do we stop now? Are we done? Well, no, because now we are looking for interesting additional effects, like the effects of special and general relativity. This is Newtonian mechanics. Kepler's laws are Newtonian mechanics. We now would like to go beyond this. We also would like to look for things outside of the black hole. Is there anything, like stellar black holes around it and so forth? Now, the right panel, by the way, is the other information we get, which is the information on the radial velocity due to the Doppler motion. Now, science often is competition. Initially, we conducted this experiment by ourselves, but then in about 1995, a group joined us working from the Keck Observatory and led by Andrea Guess at the University of California, Los Angeles. And since then, our two groups, have been in a good international competition, and that's a good thing, always, for scientists, because you see, if somebody tells you, I've seen this and I believe this, maybe you shouldn't trust that person. That's the good rule in sciences. It's only true if somebody else can prove it also. And so I show you what Andrea has measured in the yellow circles. So Andrea started a little later than me, but that's pretty much the same thing what we are seeing. So that shows you, indeed, this particular star, which has a mass of about 15 solar masses, moves around the galactic center Sagittarius star object, which doesn't radiate much other than in radio, like the planets around the sun. So this is a star moving planet orbiting around a black hole. And it's not just one of these objects we are seeing. In fact, we are now tracking thousands of stars. To not confuse it too much, I only show 13 of those, but I could show you now orbital movies for about 30 stars. And so the galactic center black hole candidate, Sagittarius star, is surrounded by an intricate dance of massive young stars. That is a puzzle, by the way, by itself. I won't talk about that, about this puzzle, but just show you that we can use these orbits now as a very detailed precision tool to explore the physics of the central region. Let me say a little more about Sagittarius star. So here's the radio emission again. That's the radio source. I told you already that the size of that object is enormously compact. In fact, what you see up here is the size, the measured radio size, as a function of wavelength. And at the shortest wavelength, in fact, in Nature last week, there was a measurement now around down here, which in fact is down here. The size is less than 10 times the expected Schwarzschild size, or the expected event horizon scale for a 4 million solar mass black hole. So this radio emission really truly comes from the region right around the event horizon. So this is indeed a very compact source. The radio observers also have made measurements on the motion of this radio source, and what they find, in contrast to the stars, is that it does not move. Now, I showed you that some of the stars move at thousands of kilometers per second. However, the radio source does not move at a level of, say, 1 or 10 kilometers per second. So clearly that means it must be very massive indeed. Let me perhaps go then to sort of summarizing what we know then about the galactic center. We have measured that mass now pretty precisely, very well. We know also as a sort of a parallel result how far the galactic center is away from us. This is in units of kiloparsecs. And we can say that indeed the apparent density of the object, of this mass, this 4 million solar mass object, must be a black hole beyond any reasonable doubt as long as general relativity holds. Maybe these are all our technical details. Let me just show you the summary of the overall measurement here. So when you plot the size of an object and its density, a normal stellar cluster is down in the right corner and a black hole is up in the left corner. And the difference between those in density, as you see, is about 20 orders of magnitude or more on the density scale. So black holes are very compact and very dense. Normal star clusters are low density. Now, in principle, of course, you could ask, well, okay, it doesn't radiate, but couldn't it be something like a concentration of rocks, Jupiters, neutron stars, white dwarfs, all very faint objects which you can't see? Why not pack them together to a density which sort of mimics what we're seeing? Why couldn't that be the case? Well, it turns out, yes, in principle you can do that, but that doesn't live very long. If you by fiat, you put an object like this together, after a very well calculatable time, it will disappear, expand, explode, and then collapse. And that time scale can be calculated for an object which is as dense as this to be less than 10 to the 5 years. And the further you go up here, the shorter lived this is. So anything up here only lives a few thousand years. That's very unlikely, of course. So what does the measurements tell us? The measurements at the present time exclude everything in this region down here. So the only thing which is left is a black hole, a speculative boson star, and a few other things having to do with false vacua and so forth, which all are theoretically very interesting speculations, but probably not realized in nature. That doesn't mean we would not like to exclude them by future measurements, but they are very unlikely. Let me come back then to the question of accretion. When talking about quasars, I mentioned that black holes are very efficient converters of gravitational energy into radiation. What about the galactic center? Does it do that too? No, it does not. The galactic center is extremely faint at any but the radio wavelength. Only in very recent times were we able to see it in the infrared. There you see on measurements here from our colleagues at UCLA, but we're making the same measurement at the VLT. We see the galactic center erupt, taking a burp, taking a zip out of the bottle once per day for about an hour or so. That's when a bunch of material, probably on the order of a mass of a comet, disappears into the black hole, and on its way, creates some energy. And that makes us understand, I don't want to explain that in too much detail here, the inner accretion region of such black holes, which is theoretically a very important issue. So the galactic center has helped us to understand really how material disappears into a black hole and why, in fact, the galactic center is so faint. But let me not get into the details. So in the last bit of the talk, I would like to now expand back to and away from us, back to the travel through to galaxies and the issue of how does it relate to galaxies, and also back to the future, so to speak, back to the situation, how did these objects actually evolve? Now, many other people have been using telescopes, especially also the Hubble Space Telescope, to look for mass concentrations in nearby galaxies, and that search has been very successful. Turns out that indeed, as I mentioned initially in the talk, almost every big galaxy has a mass concentration like the Milky Way. Many have bigger mass concentrations than our Milky Way. We are a fairly small example. Our nearby Andromeda galaxy, for instance, here, has a central concentration of about 100 million solar masses, so 30 times more than the Milky Way. And clearly, that is very plausibly a black hole, although the level of confidence is by far not as good as in the galactic center. The remarkable finding is if you plot the mass of that central object, let's call it the black hole, against the mass of the central mass of the galaxy here in logarithmic units, okay, so this is factors of 10 here, there's a correlation. So the heavier the galaxy, the heavier the central black hole. Now, when you think about that, initially that might sort of seem trivial. The taller, the heavier, and so forth. But it isn't actually, because the galaxy here does not know that there's a central black hole gravitationally. Because out here where we measure the bulge mass, the stars see mostly themselves. The mass in that central black hole is only 0.1% of the total. So the stars don't know about the central black hole, but the black hole knows about the galaxy. And it turns out that this correlation tells us something about the past. The past of the correlation, the connection between the central black holes and those galaxies. And let me explain that a little more. As you know, the speed of light is finite, and that means when we look out in space to large distances, simultaneously we look back in time. With the biggest telescopes like the VLT, we can look back now to about 9/10 of the age of the universe. And what we find is as we look from our present time, 13.7 billion years back to zero, we find that the activity of quasars, so that is accreting black holes, here in red, increases enormously by more than an order of magnitude. And so does the activity of the forming of stars and galaxies. That would be the formation process of galaxies. And the remarkable thing is that about 2 to 3 billion years after the Big Bang, the universe was totally different from what it is now. Now only every 1/1,000,000th of a galaxy is a quasar. Back then it was every 100th. Okay, so quasars, black holes, were already present at that time and were going full blast. They were being, fueled at the maximum rate possible. They were growing because of this, and so they were establishing the masses they now have. The big black holes we see in our environment now in other galaxies are the ashes of this early period. And we can see, in fact, in a few rare cases, objects, black holes of several billion solar masses, which had formed already 800 million years after the Big Bang. There's one of these cases. 800 million years. Sounds like a long time for most of us, but it isn't on a cosmic time scale. In fact, it's very hard to understand how these black holes could have easily formed in that period. Now, in computers, one can understand how cosmic structure formed from the initial fluctuation of the hot soup after the Big Bang. The cosmic microwave results are beautiful examples where we can look back to about 300,000 years after the Big Bang. And these little fluctuations in temperature of the Big Bang tells us how structure formed, and that formed in dark matter concentrations. Then when material recombined and baryonic gas came in, and this is a computer simulations of a formation of a galaxy, into these concentrations of dark matter streamed the normal matter we are made of, the baryons, hydrogen, and a few trace helium atoms, and then over time grouped together in these central regions and formed galaxies. And as you see, there's streams of material. There's also collisions of different forming galaxies. And over giga-years, then objects like our Milky Way formed out of this soup along the dark matter concentrations. That's how galaxies formed. Now, how did quasars form? Well, because the density in the early universe during the time when these galaxies formed was very high, the chance of a cosmic traffic collision between two galaxies actually was sizable. The chances was about 30% for any galaxy at that time to collide with another one. within about a gigayear. When two galaxies collide, something terrible happens. They get transformed. And as you see, what started off here as two spiral galaxies in the end is mixed together. Some gas and some stars are thrown out, and a lot of material is funneled into the very center, and what comes out is a so-called elliptical galaxy. That's done in a computer. We can actually see this in real galaxies. Here's a case, in fact, of a nearby system where we have two galaxies colliding, and you can see pretty much the same structures in the galaxy, this disrupted material. And we have here in the process two black holes which are fed in the process. So the idea is that the black holes, which already were present in these two initial galaxies, during this destruction and disturbance process, got fed at an enormous rate because the angular momentum was removed rapidly. And then in the end, what came out is a single big black hole, which then, of course, was shining for a while as a quasar, and then, however, lost its fuel supply and then became a more normal massive galaxy. Finally, then, where do we go next? I already said that we don't want to stop. In fact, we have every reason to believe that we can now go from the question, are there black holes, and what was their role, which I touched on a little bit, to the next question, can we use black holes as tools for physical measurements? For instance, to test general relativity. And that's a goal we will have in the next years. Whether we will succeed or not, we will see. But what we want to do is we don't want to use just a single telescope, but we want to connect these four big giant telescopes of the VLT together as a single super telescope, then of size 200 meters, gaining another factor of 30 or so in resolution with a fairly ambitious experiment we call gravity, where we then have the resolution, we hope, the precision of measurement to resolve the Schwarzschild radius in the galactic center and really tell whether the structure there is just, the space-time structure is just what general relativity predicts or not. And of course, the strangeness of the world of strong gravity you may have seen in pictures here. Here, in fact, this is a flat accretion disk, initially flat accretion disk observed through the central black hole, but because the light curvature is so strong around a black hole, it appears like a folded object because the light is folded back over the black hole and around it. And so this strange world of strong gravity is something which tells us exactly about the physics of the theory, and that's what we could use to understand whether or not GR indeed is the right theory, as everyone would expect it to be. So black holes are not objects of movies anymore, but in fact real objects of scientific endeavor. We have shown that they exist almost in every galaxy. We think they play an enormous role in the formation and transformation of galaxies. They formed very early on. We don't quite understand why, and we want to play with them, as scientists do. Thank you very much.
Thank you, Professor Gansel. We now welcome questions from the audience. If you have a question, please raise your hand, and I'll direct one of our helpers to bring your mic. Yes, sir. Yeah. Mic there.
Hi. I want to know, does black hole have a lifespan, or is it an eternal entity? Does it have a life?
A classical black hole, I mean, in the sense of general relativity, has infinite lifetime, okay? The only thing which shortens its life, so to speak, could be quantum effects, and that's Hawking radiation. So that energy actually escapes out of the hole due to quantum effects. Now, it turns out that for the black holes we are observing, that age, so to speak, is infinitely long, or at least it's so long that, it is much, much longer than the age of the universe. So these objects are quasi, for all practical purposes, of infinite life span. And the only thing in astronomical terms they can do is to grow, but I showed you that most of the growth happened in the past, so the future is boring.
Yes, we understand that all the galaxies, they are moving around with a center, almost like a centrifugal force. If you're using a Newtonian, so you would expect the kind of Kepler relationship between the velocity and the radius would happen. So with the modern astronomy tool, now we can estimate how large the mass is. We can estimate how small that center is, so we know what the density. And my impression is that from those measurements, we know it's a very high density, very large mass. But whether it's truly a black hole or not, do we have other convincing signature that the modern tool is able to say, yes, we can pinpoint that beyond this is a very massive center in a very small space, but there are other signatures expected by the black hole theory.
Yeah, well, okay, let me again say that, there are many phenomena you can observe from accreting black holes. Quasars are the best case, which are fantastic in its phenomenological, appearance. And any one of which those people observing it would say are, fantastic evidence in favor of a black hole. But they are sort of secondary pieces of evidence. As I tried to explain before, the true primary piece of evidence here is gravitation and coming as close as possible. So what I've shown you here, that in the case of the galactic center, we are essentially coming as close as, in the case of the radio measurements, a few times the event horizon. That's pretty damn good. That's pretty damn good. I think there is, as I tried to say, let me repeat this again, there's nothing which fits in there other than a few speculations. I'm happy to discuss these speculations with you. And a black hole solution in as long as general relativity applies. Now, you can go ahead and say, I don't believe in general relativity. That's fair. And then we talk to each other again in a few years.
I'm referring because in our case, we don't have the quasar in the center of the galaxy. So therefore, I just wonder, beyond the density of the masses, and whether using our tool, we can have additional signature.
We do.
Just wonder.
We do.
Okay.
We do. I glanced over this. Unfortunately, I didn't want to stretch out the talk too much. Yes, we do at a small scale. A small intensity scale. So we are seeing X-rays. We are seeing, radio emission. Infrared flares. We are exploring this in great detail. We can say that this hard radiation comes from a very central region, very high energy density, and so forth. So we can say a lot. It's not, of course, a quasar, but it's similar in terms of physics to what the quasar does.
Is the dark matter play any role in this case?
The dark matter.
Dark matter?
That's a very good question. Now, dark matter, we believe, might be mysterious, non-charged elementary particles, which we have not yet seen, massive particles, which are only weakly interacting. So no strong, no weak, in fact, and no electromagnetic interaction. So the only thing you would likely to see is gravitational interaction. Since gravitational interaction is very weak, if you start from a normal solution of the universe, it's almost impossible to get a concentration of dark matter through gravity alone into a small region, because there's no dissipation. You see, baryons can dissipate through all these other forces. Dark matter particles, at least in the speculation currently, cannot. So you would expect there be some amount of dark matter in these regions, but not very much. Certainly not forming the black hole, so to speak. That is not expected. It would be highly interesting, extremely interesting, to see, and that's the measurements we're trying to do right now, in the halo of this big black hole, which is sort of a attracting all of this material, including dark matter, whether there might be a spike of dark matter surrounding it. And it has theoretical calculations, how much that might be. It's a little discouraging, I should say, that we are able to see it, but it could be. But it won't dominate the mass by any means. It will be a small perturbation.
Can you perhaps give a simple explanation why we don't see accretion, a lot of accretion radiation in our own galaxy?
Yeah, well, okay, I think the trick number one, or the problem number one, as always in astronomy, is angular momentum. A black hole, as seen from the galaxy center, is this little teeny speck. And you get something in there, you have to shoot very well. You have to shoot right at it with a precision which, you will only manage in very few cases. So you have to get rid of all of that angular momentum. How do you do that? Well, you have a lot of friction. That's the trick. You have a lot of friction. How do you get friction? Well, you have a high density of material, and we believe in astronomy a high density of magnetic fields. So that it's not molecular friction which dominates, but high density of magnetic fields. So in low density plasmas, like in the galactic center, the process of friction is very inefficient. And calculations, serious computer simulations show that of 100 protons entering the sphere of influence of the black hole, only about one actually makes it into the event horizon. All the other ones don't lose enough angular momentum, they go back out. The next thing is efficiency of radiation. It turns out that at low densities, the next thing which happens is that the gas gets hot because of gravitational energy, but it doesn't radiate. And so that means that the most of the gravitational energy gets ejected into the hole rather than radiated away. And then finally, it's just the amount of material. In a quasar, you really dislodge, probably in one of these galaxy collisions, entire masses of gas of the galaxy, and some of it makes it into the center, and that lights up a quasar. Here, it trickles a little bit of that and so forth. So the density is too low. So it's a combination of effects. Yes. No, not in the galactic center, and that is a great puzzle. Now, technically, and I have to be a little technical. I discussed these measurements of the radio size. Why didn't I show you a radio image, which is something you would have liked to see, and we all would like to see. The reason is because, like in the case of us looking at the galactic center, through the Milky Way in the optical, and all being obscured by dust. In the radio, unfortunately, the seeing isn't very good toward the galactic center because there are electrons. There's electrons between us and the galactic center, and electrons act as a scattering screen of the radio waves, blowing up the image, much above what it should be. And so the best the radio astronomers can do at the sort of the wavelengths where they can image is to measure a size, but not a shape. Most radio astronomers expect to see a jet-like feature when they finally, in sub-millimeter wavelengths, do imaging, which they cannot yet do, but will do, I hope, in a few years. So the expectation is indeed this. When I said 100 protons, from 100 protons making N99 go back out, that back out is not a spherical thing. It's sort of something coming in and then probably going out in a jet-like formation.
Is it well understood by simulation or so forth for stable galaxies like our own, where there are well-defined spiral or elliptical galaxies, that you only get one center? You don't get 2 or 3 central black holes.
Yeah. Well, if you have 2 black holes and a galaxy around it, that is not a stable situation because there will be, so to speak, friction. You have a 3-body problem, and energy gets transferred. And so, in fact, that has been simulated pretty well. As long as you have a lot of material between the 2 black holes, what happens is that the black holes give orbital angular momentum to the rest of the material, which means that some of that material goes out and the black holes go in. then there's, technically speaking, there's a little bit of a problem when there's not so much material inside anymore. But in the end, gravitational waves take over, and then the two spiral in. In fact, that's something which we hope to see in about 10, 15 years from now from experiments in space, where we then hope to see across the universe galaxies spiraling in one or the other case and making that event. So no, you would not expect to see stable solutions with two black holes. But I've shown you in one of the images a non-stable situation, which is a merger. Now that has a finite lifetime. It takes about 100 million years, then it's gone. But during that time, you can have two black holes. Now, if you have three black holes, then you can get a slingshot effect, so that of the three, only two remain, or one, and the other one gets ejected back out in space. Now, is that in a process we should think about? Well, maybe, but none has been found. All the black holes which have been seen are in the centers of galaxies. But these are very interesting questions.
Now we have we have time for one more question. Sure. Of course.
Do you think the LHC is going to produce a micro black hole?
That's,
It forms while you radiation coming out.
yes, yes. That's far beyond my, pay scale, and so I cannot comment on this. But let me say, suppose it would. It would be tremendously exciting, because it would immediately, show us that hidden dimensions and string theory plays an enormous role. Because only that really would allow us to get to these scales, where gravity becomes important with current energies. Because otherwise, the grand unification is at such high energy that, LHC is not capable to do it. Now, what the probability is of seeing this, I'm sure there are some colleagues who could comment better on this than me.
Okay, thank you all again.
Thank you very much.
Kensel. The lecture session is now complete. We would like to thank everybody here for joining us.
Thank you very much.